In this video, we're going to learn about the ideal gas law. In addition to pressure, volume, and temperature, we also want to consider the amount of gas, and we're going to consider that in moles when we're talking about the ideal gas law. And so when we're talking about amount of gas, we're talking about moles. Now the moles relates to the number of molecules divided by Avogadro's constant. And so the mole is a fundamental unit. So the ideal gas law combines the macroscopic values of pressure, volume, and temperature, and it combines that with the number of moles. And then we have R here, which is the universal gas constant. We must ensure that pressure is always in pascals, the volume is in the cubic meters, N is in moles, and then this is the constant 8.31 joules per Kelvin per mole. And then like the combined gas law, we want to make sure that temperature is always going to be measured in Kelvin. In this example, we have a container holding an ideal gas. The number of molecules is doubled while temperature and volume remain constant. So what's going to happen to the pressure? And so we can set this up a few different ways. I like to use the algebra side of this and equations and set up what's going to happen. So I know that initially PV equals nRT. So that's for the initial value of the substance. And then if I double that, I know I have some new pressure. I'm just going to call it P2. It says the volume remained constant, so I can use the same variable. The number of moles is doubled, so that's going to be 2N. R remained constant, and T is constant. So what I can see here is that pressure in the initial one is nRT over V, and P2 is 2nRT over V. And I can see that this is the same as this. So I can replace that with P. So I know that the new pressure is 2 times the original pressure. So the answer is B, it doubles. Now in this question, it wasn't particularly challenging. I could have just known that if I double the number of moles, I double the pressure. But I wrote it out like this because this is a really useful way of solving these types of problems. So you can write the original in the algebra and then the final, and you can combine those, look for things you can eliminate, and get the final answer. Two containers have the same volume and temperature. Container X has twice as many molecules as container Y. Which statement is correct? So this is actually similar to what we just talked about. Container X has twice as many molecules as container Y, so it's doubled. So the pressure in X is twice that in Y. Actually, I think that's correct. The average kinetic energy of X is greater. That can't be true because the temperature is the same, so that means the average kinetic energy is the same. The molecules move faster. That's similar to B. That's not right. The pressure in X is the same as Y. Well, you can't have the same volume and temperature and then twice as many molecules. You're going to have double the pressure. So this one's not correct. So, yep, A is the correct answer here. A sealed container holds 3 times 10 to the 23 molecules of an ideal gas at a temperature of 350 Kelvin and a pressure of 1.5 times 10 to the 5 pascals. Calculate the volume of gas. So this is a ideal gas law question, but they gave me the number of molecules, which is not the number of moles. So that's not what goes in the formula. So the first thing I'm going to have to do is find the number of moles, which is going to be N over Na. So that's 3.0 times 10 to the 23 over, and then I'm going to use Avogadro's number, 6.02 times 10 to the 23. And that's going to give me a number of moles of 0.50. Now I can plug all of this. I know pressure is in the right unit and temperature is in Kelvin, which is the correct unit, so I can find the volume. So PV equals nRT. So the volume is going to be nRT over P. So the number of moles is 0.50. The R is 8.31. Temperature 350 divided by the pressure of 1.5 times 10 to the 5. And I'll plug that in my calculator and I get 9.6 times 10 to the negative 3 meters cubed. So that would be the volume of this particular gas. Pressure, volume, and temperature are measured for a fixed mass of gas. The temperature, T, is measured in degrees Celsius. The table shows the variation of PV with T. Use the data in the table to determine whether this gas behaves as an ideal gas. So what we're looking for us to use the data to prove that it's, or not prove, to demonstrate that it's behaving as an ideal gas, we're looking for this relationship, PV and T, to be linear or proportional. So what we need to do is prove that these are proportional. One way we could do this, we could graph this and see if we get a straight line. One thing I noticed is that these intervals, the x values, they go up by 20 each time. So they go up by 20, and then these ones all tend to go up by 0.3. So since they have the same common difference, or they go up by the same amount, we can say that for sure these are a linear relationship. So this is a linear relationship. But that's not quite enough to show that this is an ideal gas. Because there's one more thing. If you watch the previous videos on the gas laws combined, when you have the temperature in degrees Celsius, what you should see is that the x-intercept, so when PV is 0, the temperature should be around negative 273. So we're going to have to figure that out. We're going to have to show that that's the case. So what we need to do is we need to find the equation of this line, the relationship between PV and T, and we need to show that the x-intercept of that line is negative 273. And if that's the case, then we know it's an ideal gas, or it's behaving as an ideal gas. So how do we go about doing this? Well, the slope of this line is going to be 0.3 over 20. And so that gives me 0.015. And then we need to get the y-intercept. Well, they actually already gave us that in the data table. So when x is 0, the y value is 4.1. So the equation that I would write would be PV equals 0.015 T plus 4.1. When the PV part, the y value is 0, what is the temperature? So 0.015 T plus 4.1. So if we divide this, solve for T, we get a value of negative 273.3 degrees Celsius. So we can definitely conclude based on this data that this gas is behaving as an ideal gas. Now, ideal gases and real gases, if we want to model a real gas as an ideal gas, it has to have a low pressure. And so what I mean by low pressure is, around atmospheric pressure or a bit lower. And so atmospheric pressure is around 1.01 times 10 to the 5 pascals. So pressures around that and lower than that, we consider low pressure. So we can say a real gas is behaving ideally. We also want it when it's a low density. And so a low density would be somewhere, around 1 kilogram per meter cubed. So something a bit lower than that. Anything lower than that is maybe even up to 1.5 kilograms per meter cubed. You have a very small difference between real gas and an ideal gas. And then it's asking for also high temperatures. And so what it means by high temperatures is sort of above, 250, 260 Kelvin. So above 250, 60 Kelvin. So when we're talking about, high temperatures, we're just meaning room temperature or more. We just really don't want any sort of like super cold temperatures. At that point, real gases no longer behave in the ideal manner. So that's how we tell if we can use the ideal gas model.